Great. So we will start with our first problem. Use the epsilon delta definition to prove the limit as x approaches 1 of 6 is equal to 6. So we're starting with an easier example. So go ahead and take a couple minutes to attempt that with yourself or the people around you. Feel free to discuss. If you have a question, put your hand up, and then we will go through it together. Yeah. You want it zoomed in. There you go. Okay, we'll get started with this. So we wish to show that for all epsilon greater than 0, there exists a delta greater than 0 such that if 0 is less than x minus a, in this case a is 1, is less than delta, then f at x, which is 6, minus the limit L, which is 6, is less than epsilon. First thing we notice here, and obviously we have a function that will always be 6, it's constant, it's independent of x. So that's why this is a special case. The first thing we notice is that 6 minus 6 is equal to 0, which is equal to 0 without the absolute value bars, which is less than epsilon. And we want an epsilon that is greater than 0. So therefore, this will always be true. So we know that any epsilon value will work. So 6 minus 6 is 0, which is less than epsilon. Epsilon is any number greater than 0. So any epsilon will be satisfied here, no matter what delta we pick. Whatever it is, 6 will always equal 6. Obviously. And so that is because our f at x, which is equal to 6, is independent from x, or another way of saying that, does not depend on x. Are there any questions with that? Yeah. Yeah. I can write it like that. So for all x, there exists, or sorry, not x, for all epsilon greater than 0, there exists a delta greater than 0, where we have, whenever this is the case, so 0 is less than x minus a, or sorry, not a, in this case it's 1, is less than delta, implies that 6 minus 6 is less than epsilon. And so how he did it is then he would go through this. So you have 6 minus 6 is less than epsilon, which is equivalent to, or if and only if, 0 is less than epsilon, 0 is less than epsilon. And so then we have, that's our restriction on epsilon. This will always be true. And so because the right-hand side of the implies statement is always true, that means we can choose any value of delta up here. How would I write that? So therefore, true. There we go. Any value for delta will satisfy. There you go. Any other questions? No, moving on. I will freeze that one. Question 2. Once again, you use the epsilon delta definition to prove the limit as x approaches 3 of absolute x equals 3. So go ahead with your partner or with people around you to go ahead and attempt that question. And then in a few minutes, we will do it together. Okay, so we'll unfreeze that. So for our second problem here, once again, we wish to show that for all epsilon greater than 0, there exists a delta greater than 0 such that, so I'm going to write it in words and then also with symbols. So if 0 is less than x minus 3 is less than delta, then absolute x minus 3 is less than epsilon. So the other way to write this would be 0 is less than x minus 3 is less than delta, implies absolute x minus 3 is less than epsilon. Now, when he was doing it in the notes yesterday, he was flipping this around. So he had absolute x minus 3, and then 0 less than x minus 3 is less than delta. So this is your premise, and this is your conclusion. If this is true, then we get here. But we start with the end and work back to find x minus 3 on this side. So that's why we're always starting here, is we're going to start here, and then, oh, that is not right, is less than epsilon. There we go. So let's go ahead and do that. So we're going to start with absolute x minus 3 is less than epsilon. Okay, and so basically what we're going to do first is that if, so just as an aside, if x is greater than or equal to 0, then we can say that absolute x is equal to x. So we're going to start off with that restriction, because we notice on this side we have an absolute x minus 3. We want to find an x minus 3. And so we need to get rid of this absolute value bar. So we start off with that restriction. And so if we do that, then this becomes x minus 3 is less than epsilon. Okay. And so recall that this is the distance between x and the limit a right here. If x is more than 3 units away from 3, it's possible that x could be a negative number, which we want to avoid. Because of this, we're going to have to restrict our delta. So this restriction here is going to cause a restriction on our delta. So our delta is the difference between x and where our x value for the limit is here. So basically what we're going to have is that x minus 3 has to be less than delta, which is going to be itself less than or equal to 3. And so delta is resembling the difference between where our x value for the limit is and the current x value. So if that distance is less than 3, then x is going to be positive. So this is our first restriction on delta, is that delta has to be less than or equal to 3. Okay. Okay. Now we have made that restriction. We only need to consider non-negative x values. Yep. And so now that we have this here, we see that x minus 3 is in the same form as here. And we can just say that delta is equal to epsilon here. So, or delta is equal to epsilon. And so we've made 2 restrictions. It's going to be the minimum of the 2. So we say that delta is equal to the minimum of 3 and epsilon. All right, we each individually worked on different exercises this week. So I'm not reading my own notes, but then these next two are more similar to the other ones you've seen in class. Are there any questions on this? Yeah. Yeah. So let's do it graphically. Okay. So when we're doing our, let's just say, what's our function here? Absolute x. So that is our function. So basically our delta value is we're going to have a plus delta, a minus delta as our bounding box here for the definition of limits. And what we're saying is that if delta is less than 3, when we're placing this line, if it's 1, then it would be at 2 and 4. If it was 2, it would be at 1 and 5. If it was 3, then it'd be at 0 and 6. If it was 4, it'd be at -1 and 7. But if it's less than 3, then it's only contained in this area. It's never negative. Does that make sense? Sorry? Yeah, so basically if we're saying so right here. So if x is positive, then we can say this. So we know we can do this because what's the absolute value of 1? Well, it's 1. What's the absolute value of 2? It's 2. The absolute value of any positive number is going to be a positive number. And then what we're saying here is that since we're limiting our x values to positive numbers, that this is always going to be the distance between the bounds here. So 0 to 6 is your maximum area for delta, is less than or equal to 3. So that means if we were to say, okay, it's going to be 0, 0 minus 3 is 3, which is going to be less than or equal to 3. So basically, this is our delta is, this is a mess now. This is your delta value. And that distance from 3 is less than or equal to 3. Or sorry, less than 3. So that means at most, this could be at 0 and at 6. Yeah. So the reason we need to do that is because we're starting here and we want to get here what we have in delta here. So we need to get rid of this absolute x. So if we didn't put this restriction on, we could have this be like this, like your delta could be 4. But delta equals 4 means, okay, now we need to keep that absolute value. Or sorry, if it's absolute x, yeah, delta is less than 4. Because then we could have -1. -1 minus 3 is going to be equal to -4. And the absolute value of that is 4, which isn't less than or equal to 3. So your question again was, why do we need to get rid of these absolute values, right? Because if we put -4 here, then -3, then it's going to be -7, which isn't going to be less than epsilon. The long story short is we need to get rid of these bars in order to have this on that side. And the only way to get rid of that is if we restrict x to be positive. If we don't, then if x is negative, then absolute x does not equal x. Yeah. Where does the 3? Yeah. So here we're saying it has to be positive. If we want this to be positive, that means our delta value, so the difference between here and here. So like we have x equals 3. And so wherever we put this line is x minus delta, x plus delta. If delta, what's so funny? If delta isn't less than 3, then we're going to have some x values that are negative. And we only want positive x values. Okay, if you want to talk after class, we can. Okay, let's move on to the next question. 3. So use the epsilon delta definition to prove the limit as x approaches 0 of x e to the x is equal to 0. So go ahead and get started on that one. And then in 5 minutes, we will take it up. our question. Once again, we'll start with our definition. We wish to show that for all epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than x minus 0 is less than delta, then absolute x e to the x minus 0 is less than epsilon, or written as he would write it, x e to the x, I'm going to remove the minus 0, is less than epsilon, follows from 0 is less than absolute x, which is less than delta. Okay, so basically we want to find an absolute x on this side, which is going to get us to our delta, which is going to tell us what our restrictions on delta are. So let's go ahead and do some algebra over here. So we have x, I'm just going to rewrite it, e to the x less than epsilon. And we can separate those values here. E to the x is always positive, so we have absolute x times e to the x is less than epsilon. And so we see we have our absolute x here, so we like that, but we don't like this e to the x. So we need to find that. So we're going to have to bound e to the x, and we're going to use the left replacement rule. Here. Okay. So we're going to say e to the x is less than some value b, for some b. And we're going to have to determine what that value of b is. With this, we assume that delta is less than some value and x is less than some. Okay. We don't know what the unknown value is. We don't know what b is. So what we're going to do is we're going to assume that delta is less than 1. Why do we do that? Well, from delta being less than 1, we're going to work back and determine what value of b we can use. So that's when we start going through delta here. So if delta is less than 1, what we end up with is x from here is less than 1. And we can use the sandwich property to say that -1 is less than x, which is less than 1. And then we can take everything and put each one of these terms to the power of x. So e to the -1 is less than e to the x, which is less than e to the 1. And we know that e to the -1 is greater than 0. So what we want ultimately is some b value so that e to the x is less than or equal to b. Or sorry, yeah, less than or equal to b is valid. Well, what if we chose e to the 1 as our b value? Then let's check it out. So we go with e to the x is less than or equal to that b value. Let's sub it in. Or sorry, let's sandwich property at first. B, sorry, -b is less than or equal to e to the x, which is less than or equal to b. And then let's sub in our b value of e to the 1. So negative e to the 1 is less than or e to the x, which is less than e to the 1. And Okay, and we were looking for e to the x here. We guessed for a b value here, which got us to this. And we know that that's true because of this. So how did we get here again? We started with our delta is less than 1. And then we transformed this to get e to the x. So we know this is true. And then we guessed that this will be our b value. And when we sub it in, we get this still to be true. So therefore, our b value is going to be e to the 1, or just e. Freeze. So now we're going to return to the proof. Our last line, which I'll write out, x e to the x, thank you, is less than epsilon. We just found out that e to the x, which is always positive, is going to be, so we have from the previous page, e to the x is less than or equal to e. So we're going to go ahead and sub that in. So we have x, sorry, right, which is, yeah, x is less than epsilon over e to the x. So x is less than epsilon over e. And so that is our potential value for delta. So delta is less than epsilon over e. And our previous restriction here was that delta is less than 1. And that's how we got our bound for e to the x. Therefore, delta is the minimum of 1 or epsilon over e. Okay, because we only have 10 minutes left, I'm just going to jump right into the next question. If you have questions afterwards, just come up to the front. We'll head outside somewhere and I can answer them. Question 4. So use the epsilon delta definition to prove the limit as x goes to 5 of 3 over x minus 4.9 equals 30. And we'll go right into the solution. Okay, we wish to show that for all epsilon greater than 0, there exists a delta greater than 0 such that, and then we once again, we will use, I'll just jump right to the way he does it in class. 3 over x minus 4.9 minus 30 is greater than, is less than epsilon, duh. And that comes from 0 is less than x minus 5, which is less than delta. Okay, with our other examples, our goal was to get an x minus 5 on this side of the equation. And there's no obvious x minus 5 there. So what I'm going to do right off the bat is I'm just going to start doing some algebra. So let's write it out. 3 over x minus 4.9 minus 30 is less than epsilon if and only if I'm going to take this denominator and multiply it at the top and bottom of the negative 30. So 3 over x minus 4.9 minus 30 x minus 4.9 over x minus 4.9 less than epsilon. Now, since they have a common denominator, I can combine the numerators. So I have 3 minus 30 x minus 4.9 over x minus 4.9 is less than epsilon, which gives me 3 minus 30x plus 147, which is 30 times 4.9, over x minus 4.9 is less than epsilon. Let's combine the values without x's. So that gets me negative 30x plus 150 over x minus 4.9 is less than epsilon. And so now what I'm going to do is I'm going to factor out a negative 30. If I do that, I'm going to find an x minus 5, which is my goal. So that gets us to minus 30 times x minus 5 over x minus 4.9. Yes, thank you. Is less than epsilon. And so I have a negative 30 in here. If you have a negative value within the absolute value bars, it's just going to become positive because all you care about is the magnitude of the number. So I can actually take that out and just make it 30. So, well, let's do that in 2 steps just so it's clear. So that is going to be 30 x minus 5 over x minus 4.9 less than epsilon. So 30 x minus 5 x minus 4.9 is less than epsilon. And same thing when you have a numerator denominator, the absolute value of the quotient is the same as the absolute value of the individual numerator and denominator divided by each other. So that written out is 30 x minus 5 over x minus 4.9, just less than epsilon. And once again, I have x minus 5, 30 is just a number, that's fine, but I still have this x minus 4.9. And so that's our issue here. So I'm just going to rearrange to put everything on the right-hand side, except the x minus 5. X minus 5 is less than epsilon times x minus 4.9 over 30. Okay, so then we have to stop and we have to do something with x minus 4.9. So that is what we will do. Oh, I'll freeze that first. 4 minutes, we got this. Okay. So because we had it as a denominator here, we already have the restriction that x minus 4.9 cannot be 0. So let me write that. X minus 4.9 cannot equal 0 because can't divide by 0. Okay. And we know, therefore, that delta must be less than the difference. Sorry, we don't know this. Because this can't be 0, we have to do this. Less than the difference between 4.9, and 5. Yep. Thank you. So that x minus 4.9 does not equal 0. Remember, delta is the difference from 5, right? So we have 5. It would be much easier to graph it out. I don't have time. I recommend looking at a graph of this. We're just going to keep going, and then I'll post the solutions. So therefore, assume that delta is less than 0.1. And so we want to find x minus 5 less than delta from our previous page. Therefore, we need to replace x minus 4.9 with the right replacement rule. That rule states that x minus 4.9 is greater than or equal to some value b. So the left replacement rule uses a less than sign, right replacement rule greater than sign. And we need to find this b value. Okay. And we're going to use our constraint here. So use delta is less than 0.1 constraint. And now the other thing is, if we used this restriction, we would actually get a b value of 0. I don't have time to show you that, but there is a video that was posted yesterday that has another example that goes through that. And I'll include that in the PDF or something. So we're going to actually choose a more restrictive constraint. So we'll say delta is less than 0.05. This gives x minus 5 less than 0.05. Okay. And so we're going to take this and then get it to be the x minus 4.9, and that will give us what our b value is. So we start from here. X minus 5 is less than or equal to 0.05, which sandwich property minus 0.05 is less than or equal to x minus 5, which is less than or equal to 0.05. We add 5 to every term. So 4.95 is less than or equal to x, which is less than or equal to 5.05. And then we're going to subtract 4.9 from every term so we can get to here. So 0.05 is less than or equal to x minus 4.9, which is less than or equal to 5.05, or no, 0.15. Okay. And here we have that x minus 4.9, which is always positive in this range. So that's why we can take this and put it in where the absolute value bars are, is always greater than 0.05. And that's what we needed to show. So we found our b value. It happens to be the same as what we set for delta restriction. Okay, a few more lines. Since x minus 4.9 is greater than or equal to 0.05, we can say x minus 4.9 is greater than or equal to 0.05. Okay, and now we're going to go back to our proof. The last line in our proof was x minus 5 is less than or equal to epsilon x minus 4.9 over 30. And basically now we can sub in this here, which is less than or equal to epsilon 0.05 over 30. And this is our other restriction for delta. So we're now in, let me just write it in one line. So x minus 5 is less than epsilon 0.05 over 30. This is from our definition here. So we found another restriction for delta. So our two restrictions are delta is less than epsilon times 0.05 over 30, or epsilon is less than 0.05. And this came from having to do the replacement of this. It is right here. So therefore, delta is the minimum of 0.05 and epsilon times 0.05 over 30. Okay, we are over time. If you have any questions, you can come up to the front after, and we're gonna go outside once I'm done packing up. Other than that, have a good day, and we will post this.